Hello, welcome to the course PH5 BO6 Electrodynamics 2. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. Today's class we are going to revise chapter 6 from Griffiths, Magnetic Fields in Matter. In the last class I introduced the concept of magnetic dipoles. A current carrying loop is known as a magnetic dipole, and the product of current and the area of the loop is known as the magnetic dipole moment. Every material in the world consists of such magnetic dipole or such current carrying loops. Now you may be wondering, what is this current I am talking about? If you take a conductor and apply a potential difference, then there is a current set up in it. This is known as a free current. But when I have an insulator like glass, where is the current here? If you want to understand what is the current I am talking about, you need to look at the microscopic structure of a material. Every material is made of atoms, and inside atoms you have electrons. And these electrons are not stationary, they are moving around. And a moving electron constitutes current, we know that. Now there are two types of motion for an electron. One, it's orbital motion around the nucleus. And second is the spinning motion about its own axis. So whether an electron is orbiting around a nuclei or it is spinning about its own axis, it is tracing out a current carrying loop. In other words, in both cases, I can imagine that electron is associated with a magnetic dipole. So dipole associated with the orbital motion is known as orbital dipole, and the dipole associated with the spin motion is known as the spin dipole. Now, since every material consists of atom, and inside every atom there are magnetic dipoles, can I say that every material is magnetic? No, right? Because you know only certain materials show magnetic properties. Now what is the reason? Because usually, even though every material has magnetic dipoles, they are aligned in random direction. So in normal condition they cancel out each other and you have zero net magnetism. But if you apply an external magnetic field, the dipole get aligned in a preferred direction, and this results in what is known as magnetization, or you can say that the material is magnetized. And depending on the orientation of magnetization, you can classify materials as paramagnets, diamagnets, and ferromagnets. In the case of paramagnets, the magnetization is parallel to the applied magnetic field. On the other hand, in the case of diamagnets, magnetization is anti-parallel to the applied magnetic field. Now, ferromagnets are similar to paramagnets, where there is a net magnetization in the direction of the applied magnetic field. But the main difference is that in the case of ferromagnets, even if you remove the external magnetic field, a part of the magnetization is retained. So these are the materials which are used for making permanent magnets. On the other hand, in the case of paramagnets and diamagnets, once you remove the external magnetic field, the magnetization is completely lost. Similar to an electric dipole, which is kept in an electric field, a magnetic dipole kept in a magnetic field also experiences a torque. Now, the torque experienced by a magnetic dipole of dipole moment small m is given by m cross b. If you recall the equation from the electrostatic, the torque experienced by the electric dipole was P cross E. So equation remains almost similar. Now in the light of this torque, now you can explain the paramagnetism happening in material. If you look at the electronic arrangement of atoms, you know that they follow a famous law known as Pauli's exclusion principle. So in an atom there are different energy levels, and maximum 2 electrons can occupy the same energy level provided they have opposite spins. Now there is a magnetic moment associated with the spin motion. Since 2 electrons have equal and opposite spins, their magnetic dipole moment get cancelled. So if a material has even number of electrons, all the spin dipole moment cancel each other and you have a zero net magnetization. On the other hand, if the material consists of odd number of electrons, now the last electron is unpaired, meaning its spin magnetic moment remains uncancelled. So when this kind of a material is kept in an external magnetic field, the magnetic dipole of the last electron, they experience a torque given by m cross b, and this dipole gets aligned in the direction of the magnetic field. Now a bulk material consists of a large number of atoms. In each atom there is one unpaired electron, so you have a large number of magnetic dipoles aligned in the direction of the magnetic field. So paramagnetism is due to torque on dipoles associated with spin of unpaired electrons. Now, what is the reason behind diamagnetism? First of all, diamagnetism is a phenomenon which is much weaker compared to paramagnetism. So in a material, if you have both paramagnetism and diamagnetism, diamagnetism will be completely masked by paramagnetism. If you want to observe diamagnetism, you need to create a situation where paramagnetism is completely absent. So I have already told you, if a material consists of even number of electrons, all the spin dipole cancel each other and you have zero paramagnetism. So diamagnetism is usually exhibited by materials which contain even number of electrons. Now electron has, in addition to spin dipole, an orbital dipole. When you place a diamagnet in an external magnetic field, what happens is that the orbital speed of electron changes due to the application of the external magnetic field. This results in a change in the orbital magnetic moment of the electron. Now this change in the orbital magnetic moment always takes place in the opposite direction of the magnetic field. So usually the orbital magnetic moment of different atoms are aligned in different direction. So normally they cancel, but when you apply an external magnetic field, each atom acquires an extra bit of orbital magnetic moment in the opposite direction of the applied field. As a consequence, you have a net magnetization opposite to the applied field. So this results in diamagnetism. So in summary, paramagnetism is due to the spin magnetic moment and diamagnetism is due to the orbital magnetic moment. The force experienced by a magnetic dipole placed in an external magnetic field is given by grad m dot b, and the associated potential energy is given by minus m dot b. Now, when a material is completely magnetized under the application of an external magnetic field, you have magnetic dipoles all over the material. And if you take magnetic dipole moment per unit volume, this is known as magnetization density or simply magnetization. So this is an important parameter in describing magnetic effects of material. Now let's quickly calculate what is the field or the potential associated with a magnetic dipole. So this is given by the Biot-Savart law. So if I have a magnetic dipole with moment small m, at a distance r from this magnetic dipole, the magnetic potential is given by A of R equal to mu naught over 4 pi m cross r cap by r square. Now if you want to calculate the total field or total potential due to magnetic dipoles of the entire material, you take a volume element and do an integration. Now in this case you can represent dipole moment in terms of magnetization density and rewrite the equation of A of R equal to mu naught over 4 pi integral m of r prime cross r cap by r square d tau prime. Now this prime notation indicates that this is the source element. Now you can apply the product rule and expand this integral. You have two volume integrals. One of the volume integrals you can convert into a surface integral using the Gauss theorem. So the expression for the net potential is A of R equal to mu naught over 4 pi volume integral del prime cross m of r prime d tau prime by r plus mu naught by 4 pi closed surface integral m of r prime cross dA prime by r. Now the first term here, this represents potential due to a volume current given by curl of m, and this term corresponds to potential due to a surface current given by m cross n cap, where n cap is a unit normal vector. So what this equation means is that the potential and hence also the field of a magnetized object is same as that produced by a volume current JB throughout the material plus a surface current KB on the boundary. Now when I say current, these are not free current which can freely move throughout the material. We are talking about electronic movement within each atom. So since electrons are bound to each atom, the current is also bound to each atom. That's why we use a subscript B to indicate that this is volume bound current. Similarly, this is surface bound current. What is the physical meaning of the bound current? Let's take a thin slab of a magnetized material. Now inside each atom there are magnetic dipoles represented as current carrying loops. So you have current carrying loops all throughout the material. Let's look at the direction of the current. If you take two adjacent magnetic dipole, here current is flowing in this direction. In the neighboring dipole, current is flowing in the opposite direction. So I have equal and opposite current. These two current cancel. Similarly, if you take next two magnetic dipoles, these two current cancel. In other words, all the internal currents cancel each other and you have only the current which are flowing close to the boundary. So it's as though you have a tiny strip of current flowing along the boundary surface. Now if you take this current by perpendicular width, this gives rise to a surface current KB. On the other hand, if the magnetization is non-uniform, then some of these internal currents do not cancel each other. In that case, you have current throughout the material, not just the boundary. This gives rise to a volume current curl of M. So uniform magnetization gives rise to surface bound current and non-uniform magnetization gives rise to volume bound current. Let's generalize our understanding now. Now we know that there are two types of current, just like the two types of charges we have seen in the last chapter. So one is the bound current given by JB and other is the free current given by JF. If you recall the Ampere's law, curl of B equal to mu naught J, let's rearrange the terms and write 1 over mu naught curl of B equal to J. Now J can be written as a combination of free current plus bound current. Substitute for bound current. So this will give you 1 over mu naught curl of B equal to JF plus curl of M. On both sides I have curl terms. So let me combine them together and write curl of B by mu naught minus M equal to JF. Now this term inside the bracket 1 over mu naught B minus M. This is an important parameter known as the auxiliary field. Sometimes people assign more importance to auxiliary field than the external magnetic field because auxiliary field is a consequence of magnetization happening inside a material. So the auxiliary field can tell you a better inside story of a material than the external magnetic field. So if you go back to this equation, the term inside the bracket is now H. So Ampere's law can be written as curl of H equal to JF. This is Ampere's law in the differential form. Now using Stokes' law, you can rewrite this equation in the integral form. So Ampere's law in integral form reads as integral H dot dl equal to IF enclosed, where IF enclosed is the total free current enclosed by the loop. Now the role played by auxiliary field here is same as the role played by the displacement field in the case of electrostatics. So in the case of displacement field, you wrote divergence of D equal to rho F. In this case, you can write as curl of H equal to JF. In both cases, you are rewriting the equation in terms of the free charge density and the free current density. This is very, very important, especially if you are considering the practical aspect, because in a material system, the only thing which you can control directly are the free currents and the free charges. So if you write equations in terms of free charges and free currents instead of the total charge and total current, practically it makes more sense. Now we can rewrite the boundary condition in terms of the auxiliary field as, if you remember, the perpendicular component of the magnetic field is continuous. Hence, H perpendicular above minus H perpendicular below equal to minus M perpendicular above minus M perpendicular below. Similarly, H parallel above minus H parallel below equal to KF cross N. So either you can define boundary condition in terms of the magnetic field or the auxiliary magnetic field. Now usually if you look at the utility point of view, the electric field E is more useful than the displacement field D, because how do you generate electric field? You apply a potential or a voltage, because voltage is something which you can directly measure, and once you know voltage or potential, you can easily calculate the electric field. On the other hand, if you want to calculate the displacement field, then you should know more details about the material under study. In the same way, suppose you want to make an electromagnet. What do? You take a coil, a wire, and pass current through it. And current is something you can measure directly, and once you know current, you can calculate the auxiliary field directly. On the other hand, if you want to measure the magnetic field, then you need to have more details about the material under study. So from a practical point of view, the auxiliary field is more useful than the magnetic field B, just like the electric field E is more useful than the displacement field D. Since magnetization is induced by the field, you can write magnetic field magnetization M is proportional to auxiliary field H, and the proportionality can be replaced by a constant chi M, where chi M is known as magnetic susceptibility. This is a material parameter, and typically it's negative for diamagnets because here magnetization happens opposite to the applied field. And for paramagnets, the susceptibility is positive because magnetization happens in the direction of the magnetic field. Now you can write from the definition of auxiliary field, you can write B equal to mu naught into H plus M. N can be written as chi m into H. So B equal to mu naught 1 plus chi m into H. This term mu naught into 1 plus chi m is known as mu, or permeability of the material. So you can write magnetic field B equal to permeability multiplied by auxiliary field H. Before concluding, let me talk a bit about ferromagnetism. So as I said, ferromagnets are materials used for constructing permanent magnets because they have a capacity to retain the magnetization. So the main difference between ferromagnets and paramagnets or diamagnets are: ferromagnets consist of small regions known as domains. Now, inside each domain, there is a perfect alignment of magnetic dipoles. So if you zoom into a particular domain, you find that all the magnetic dipoles are aligned in the same direction. But if you take two different domains, then among them, the alignment of the magnetic dipoles are completely random. So inside each domain, there is perfect alignment, but between two domains, there is a random alignment. So if you look at the material in totality, since all the domains are arranged randomly, there is zero magnetization. But when you apply an external magnetic field, what happens? There are already a few domains which are in the direction of the external magnetic field. What they do is they induce a similar ordering in their neighbors. So the neighboring domains also get aligned in the direction of the external magnetic field. Now they in turn induce ordering in their neighbors. So slowly the domains which are along the direction of the external magnetic field, they grow in size, and other domains they shrink, and finally one single domain takes over the entire material. So the entire material gets aligned in one single direction, and in this case you can say that the material is completely saturated. Now if you remove the external magnetic field, what happens? Some of the domains, they go back to their original random alignment, but majority of the domains retain their magnetization. So you have a net non-zero magnetization. So this can stay in the material for a very long time. That's why these materials are known as permanent magnets. Now, if you want to study the ferromagnetic property of a material, you can take a coil and pass current through it. It generates a magnetic field. Inside the coil, you place the ferromagnet. Now you can measure magnetization of the material as a function of current or the applied field. This plot is known as hysteresis plot or hysteresis loop. So let's start with the initial stage where there is zero current and zero external magnetic field. The domains all are arranged in a random direction. So there is a zero net magnetization. You slowly apply the current, an external magnetic field is set up, domains are slowly getting aligned in the direction of the external magnetic field, magnetization is slowly growing in size, and finally you reach a point where all the domains are arranged in the same direction, the material is saturated. Now from this point, if you reduce the current or reduce the external magnetic field, some of the domains go back to the original configuration, but most of the domains retain their magnetization. So in this region, the material acts as a permanent magnet. If you want to kill off the magnetism in a permanent magnet, what do you need to do? You need to supply current in the opposite direction. So the magnetization decreases, and finally at this point magnetization becomes zero. Material comes back to its original configuration. Now if you continue to increase current, magnetization grows in the opposite direction. Then the same story repeats, it gets saturated, and if you remove the magnetic field, some of the magnetization is retained. Once again, in this region, material acts as a permanent magnet. So this is known as hysteresis loop, and this kind of a plot is fundamental in understanding the magnetic properties of a ferromagnet. That's it for today. Thank you.